Hi everyone, it's Miss H, and today we're going to be looking at graphs associated with motion. So we're going to start looking at position time graphs. And a position time graph, time goes on the x-axis. It's usually going to be measured in seconds, but it could be minutes, hours, days, any unit of time. Position will go on the y-axis. It's usually measured in meters, but again can be in centimeters, kilometers, any measurement of distance or position or displacement. The data is continuously taken over time, so we typically will use a line graph, which means that we do connect the dots to each other. But occasionally when we're doing certain types of labs or that sort of thing, we might actually be technically doing a scatter plot instead of a line graph, so we might have to add a line of best fit just to help us straighten out some of that data or smooth some of that data out. The slope of a position time graph, so rise over run means change in position over time, and as we learned in our previous video, change in position over time is velocity. So the slope of a position time graph gives us the velocity of the object. The number of directions that the object moves in comes from the velocity, so if they're all positive or all negative, it moved in one direction. If they're both positive and negative slopes, then it means that you have two directions. That's the maximum number of directions you can show on a position time graph is two directions. It can either go positive or negative, that's it, nothing else, or stand still. So how do you know whether it's positive, negative, or standing still? Well, a horizontal line means that the position is not changing, so the object is standing still or not moving. The time still goes on, but the position does not move. A straight line means that it has a constant velocity, so if that straight line is horizontal, that constant velocity is 0. If that straight line has a positive slope, then it is moving in a positive direction. If the straight line has a negative slope, then it is moving in the negative direction, and therefore is a negative velocity. If that is towards the x-axis, meaning that it is in quadrant 1, then it is moving toward that arbitrary 0 point, that observer, that line that we kind of use as our reference. And if it's moving away from the x-axis, then it means that it is moving in away from that arbitrary 0, that observer. And so that would either be a positive slope in quadrant 1 or a negative slope in quadrant 4, whereas toward the x-axis would either be a negative slope in quadrant 1 or a positive slope in quadrant 4. Because we can't go backwards in time, we don't use quadrants 2 and 3. So let's take a look at a position time graph here. So I'm going to label a couple of points on this just to help us to see things a little more clearly. So we have A, B, C, D, E, and F. So our positive slopes, so let's look at, okay, A to B has a positive constant velocity. Okay, it is moving away from the axis. So it's moving away from the x-axis, the time axis. From B to C, it's standing still. Or not moving because it's horizontal. From C to D, it has a negative constant velocity, and it is moving toward the x-axis. From D to E, whoops, that should be D to E. It has a negative constant velocity, moving away from the x-axis. And then from E to F, it has a positive constant velocity, and it's moving toward the x-axis. So that's just looking at kind of what's the object doing. So it moved away from the observer in a positive direction, then it stood still, then it moved toward the observer in a negative direction. It continued walking past or moving past the observer in the negative direction, and then about faced and came back to the observer. So that's kind of the idea of what you're looking at here. Now the other thing we need to know about is how to actually calculate the slope of the line. So again, I'm going to label my points here. So calculating the slope is simply rise over run. So from A to B, our rise is 60 meters minus 0 meters over 10 seconds minus 0 seconds, which gives us 60 over 10, or 6 meters per second. From B to C, we are horizontal, so it's 0 meters per second because it's horizontal. And so you can see that your rise is going to be 0, so 0 over 5 would give me 0, so I could have done it that way as well. From C to E, I'm going to skip over D just because C to E is all one line. So from C to E, I have negative 40 meters minus 60 meters over 40 seconds minus 15 seconds. And so that gives me negative 100 meters divided by 25 seconds, which gives me negative 4 meters per second. And then from E to F, I have 0 meters minus negative 40 meters over 55 seconds minus 40 seconds, which gives me 40 meters divided by 15. And 40 divided by 15 gives us 2.7 meters per second. So you can see that the slope of the line, the steeper the slope is, the higher the velocity is. The flatter the slope is, the lower the velocity is. So the closer you get to vertical, the higher your velocity is. The closer you get to horizontal, the lower your velocity is, the closer you get to 0. On a position time graph, a curved line, which we didn't see on the previous one, means that the object is accelerating or changing velocity because the velocity is no longer constant, it's changing at a different rate. So if that line is getting steeper, it's speeding up. If it's getting flatter, it's slowing down. If it's curved up, it's positive acceleration. If it's curved down, it's negative acceleration. So the 4 ways that we can see acceleration would be curving up, getting steeper, so that one is speeding up, getting steeper, or rather this is positive acceleration and speeding up. Okay, this is negative acceleration and speeding up. Okay, this is positive acceleration and slowing down. This is negative acceleration and slowing down. So you can see that there's 4 different kind of curve shapes, and of course those curves can be steeper or less steep, but basically we're looking at it's not a straight line. So we don't actually know how to calculate the slope in this class anyway. We don't know how to calculate the slope of a curve. Some of you will be watching this video for other classes and will know how to do that, and so your teacher can explain that to you. But for our classes, we don't deal with how to calculate the slope of a curved line. So what we need to do is look at a velocity time graph. So velocity time graphs, time goes on the x-axis again. It's usually going to be measured in seconds, but could be any time unit. Velocity goes on the y-axis. It's usually going to be measured in meters per second, but could be any distance unit over any time unit. But the time unit does have to be the same as the x-axis time unit. The data is again taken continuously over time, so we're typically going to use a line graph where we connect the dots. And the slope is rise over run, which is change in velocity over time, and change in velocity over time, as we'll talk about next, is acceleration. So if you have a horizontal line on a velocity time graph, that means that your velocity is constant because your velocity is not changing. Remember, your velocity is now what's on the y-axis. So your velocity is not changing if it's a horizontal line. That means it has constant velocity. If that horizontal line is on the x-axis, then the velocity is 0 and the object is not moving. Any straight non-horizontal line represents acceleration. If that is towards the x-axis, it is slowing down. If it is away from the x-axis, it is speeding up because your x-axis again is 0. The number of directions is provided by whether the velocities are positive or negative. If all of the velocities are positive or if all of the velocities are negative, then only one direction of motion occurred. If you have both positive and negative velocities, then 2 directions occurred. And again, 2 directions is the maximum number you can show here. So you're not going to see a curved line on a velocity time graph. You're only going to see either a horizontal line or a straight line that is not horizontal. So let's take a look at this example. So here we have an example of a velocity time graph, and it looks very similar to our position time graph, but it means something entirely different now. So we're going to label the points the same way: A, B, C, D, E, and F. But these points now mean something a little bit different. So from A to B, the object is experiencing positive acceleration. Okay, from A to B, the object is experiencing positive acceleration. So it's accelerating in a positive direction, and it is also itself a positive number because of, again, that rise over run being in a positive direction. From B to C, the object has a constant velocity, and it's positive. Okay, so from B to C, it has a constant positive velocity of 60 meters per minute. From C to D, it has a negative acceleration, okay, and is slowing down because it's approaching the x-axis. So from A to B, it's speeding up. And from C to D, it's slowing down. Okay. Then from D to E, it's also a negative acceleration. Okay, but now it's speeding up again. It's just that what's happened is that the direction is now negative. And so it's moving in that negative direction now, and it has a negative acceleration. So negative direction plus negative acceleration means speeding up. Positive acceleration plus positive direction means speeding up. Positive acceleration and negative direction, or negative acceleration and positive acceleration, means slowing down. So then E to F is positive acceleration, but it's slowing down. Okay. So that's our velocity time graphs. Again, these are a little bit different in that there's what tells you the number of directions is whether you have both positive and negative velocity. So this object did move in two directions because we see both quadrants 1 and 4. If I only saw quadrant 1 or only saw quadrant 4, I would only have one direction of motion.